IEEE VTS Young Professionals webinar. Uh, we are here after long break, but today we have a young professional who is part of IEEE and VTS, and he will be talking about AI enhanced scheduling algorithm for distributed C V2X communications. His name is Luca Lasvargi. I will invite him on the floor. Welcome, Luca.
Hi, Tamur. Thank you for the introduction.
Thanks a lot. And just one moment, I would like to explain one thing that the webinar will be around 40 to 45 minutes, and then we will have an last 10 to 15 minutes for the question and answers. So before going to the webinar, I would like to thank Luca and VTS for giving us the opportunity to organize this webinar. So welcome, Luca, and please, floor is yours. Thank you.
Thank you, Tamur. So good afternoon, everybody. With today's presentation, I would like to share with you the details of my work, my PhD work that I carried out at the University of Modena Reggio Emilia, and then I am actually pursuing right now in my new position at the UI Core Laboratory of the University of Miguel Hernández of Elche in Spain. So a short quick information about myself. I got my master's and PhD degrees at the University of Modena Reggio Emilia in Italy. During my PhD, my research activity has been mainly focused on the study, the dimensioning, and the optimization of distributed C V2X communications. And basically, I tackled the study of C V2X communications from three different perspectives: simulations, analytical, and experimental. And in particular, during my PhD, I developed the first open source simulator of C V2X communications. And actually, I leveraged this simulation tool to propose and assess the first AI-enhanced scheduling algorithm for the dissemination of aperiodic traffic, which will also be the core of this presentation. As I said before, I currently am employed at the University Miguel Hernández de Elche, UMH, where I am a postdoc researcher working on C V2X communications. And if you want more information about my papers and my current status, you can find them on Scholar and my LinkedIn profiles. So let's get started with the presentation. The outline of this presentation will be as follows. I will start with a quick introduction on vehicular communications, and then I will give you some more details about C V2X sidelink, so the specific cellular technology that I have analyzed during my PhD. I will also give you some details about cooperative awareness messages, that, as we will see, is the type of aperiodic traffic that is actually the focus of this presentation. And then I will show you the details of the AI enhanced distributed scheduling that I have developed for the dissemination of this particular type of traffic. And finally, I will draw some conclusions, and I will present you some possible future research directions that inspired by this work. So let's start with the vehicular communications. And let's start with a simple question. Why? Why vehicular communications? As you might know, currently autonomous vehicles rely on a complete suite of powerful sensors to perform their autonomous driving tasks, like radars, lidars, cameras, inertial measurement units, and GNSS receivers. However, vehicle-to-everything communications, or V2X communications, have two main advantages over this powerful and exhaustive suite of local sensors. Vehicular communications can achieve a longer range with respect to local sensors, and they can also work in non-line-of-sight conditions. And the ultimate goal of V2X communications is to increase road safety and improve road transportation efficiency by allowing the deployment of new use cases like traffic jam warning, left turn assist, or vulnerable road user protections. Or, as I reported in this slide, typical use cases are forward collision warning and do not pass warning, where you can see that actually V2X communications are able to provide an advantage with respect to the limitations of local sensors. So what type of cooperative and connected automated mobility, or CCAM, applications can be supported with V2X? Actually, we can identify three different phases. The first phase, also called awareness driving, where connected and autonomous vehicles will transmit basic information like the speed, the position, and the heading of the vehicles to inform neighboring connected and autonomous vehicles about their presence. Then, and this is actually the phase that we are currently in, because some OEMs already equip their vehicles with phase one enabled V2X modules. And then in the near future, we foresee the evolution towards a phase two, or called cooperative perception phase, where connected and autonomous vehicles will transmit information not only about their own status, but also about the objects detected using their onboard sensors to actually extend the field of view of their neighbors beyond the onboard sensors range. And in the future, we will also have a phase three, or cooperative driving phase, where CAVs will use V2X communications to also share their driving intentions and coordinate their maneuvers. So as you can see, V2X communications can really improve the road safety and transportation efficiency. But how can vehicular communications be supported? We currently have two main competing technologies for V2X. One on the left of this slide, called ITS G5 in Europe, or DSRC in the US. And on the right, the C V2X technology, which will be the main focus of the presentation. As you can see, these two technologies share the upper part of the protocol stack. They include the same layers. Also, when it comes to security, they support same security operations, same non-safety applications, and same safety applications, and which are actually deployed through a common facilities layer with a common design. The main difference between these two technologies lies at the lower layers of the stack. Actually, as you can see, the MAC layer and the physical layer of the two technologies is significantly different. And although the SRC, since it's is based on Wi-Fi, basically, it is a technology that has been very well studied over the years. And then after several years of simulations and experimental testing, whereas C V2X is a more recent technology, and that's why it has been the focus of my PhD. In the C V2X technology, we can have three types of communication mode: unicast, groupcast, and broadcast. And in general, vehicles can communicate through infrastructure communications, where vehicles reutilize the uplink and downlink interfaces used for cellular communications to share their V2X data. Or we can have distributed communications. Distributed communications take place over a dedicated sidelink interface that has been designed specifically for vehicle-to-vehicle communications by 3GPP, and that allows vehicles to directly communicate and exchange data without the support of the cellular infrastructure. And actually, the sidelink interface is considered as the baseline interface for safety communications that should not depend on the availability of the cellular network. And it has also been the focus of my research work. So how is this sidelink interface design? What are the main characteristics of the MAC and the physical layers? Let's start with a short overview of C V2X sidelink communications. The first version of it was designed in 2017 with LTE specifications, and actually was called LTE V2X sidelink. And its design was initially meant to support basic safety-related applications, such as the phase one awareness driving use cases that we mentioned before. And then in 2019, with under the 5G umbrella, we had a new release called New Radio V2X Sidelink, which is designed to support more sophisticated, enhanced V2X use cases like platooning, cooperative perception as part of the phase two, and cooperative driving as part of the future phase three. A main characteristic of the newest new radio V2X side-link technology is that it is not interoperable with its predecessor, LTE V2X side-link, and at the same time features a wide range of novelties. Among the novelties, we can list for sure a more flexible physical layer, a more flexible management of radio resources, a new reevaluation mechanism, a new preemption mechanism, and also the support of HRQ-based retransmissions. And from the MAC layer perspective, we have two resource allocation modes that have been basically inherited by its LTE V2X predecessor. Okay, with respect to the resource allocation modes, as I mentioned before, at MAC layer, connected and autonomous vehicles can employ two communication modes to select their transmission resources. The first communication mode, or called NeuRadio V2X Mode 1, is a network-assisted strategy that requires cellular coverage to operate. According to it, vehicles ask the coordination of the cellular infrastructure to select collision-free resources and operate in a collision-free manner. On the other hand, we have NeuRadio V2X Mode 2, which is a distributed strategy that operates also in out-of-coverage scenarios. And as I mentioned before, for this reason, NeuRadio V2X Mode 2 is considered as the baseline V2V mode, so the baseline mode for vehicle-to-vehicle communications, as safety-related applications cannot depend on the availability of the cellular infrastructure. In NeuRadio V2X Mode 2, in particular, connected and autonomous vehicles autonomously select their transmission resources without relying on the cellular infrastructure by employing what the so-called semi-persistent scheduling scheme, which is inherited from LTE V2X specifications with minor modifications. And this SPS scheme is what allows vehicles to basically autonomously select their transmission resources and coordinate their transmissions in a collision-free manner, or at least they try to operate in a collision-free manner. How does it work? As I said before, the SPS scheme is a completely distributed strategy which is based on a sensing and on a selection phase, where the generic CAV is autonomously learning which radio resources are already in use by its neighbors. The selection and the reservation of transmission resources in the SPS is performed by a resource reselection mechanism that works as follows. When a vehicle generates a new packet at slot SG1, indicated in this slide, it first opens a selection window that includes the set of candidate resources for selections. Candidate resources for selection are called a subchannel, which is a group of resource blocks in the frequency domain able to fit the transmission of the generated packet. And in order to identify the collision-free resources inside the selection window, the vehicle monitors the resources employed by its neighbors during a previous sensing window that lasts 1 second. In this sensing window, the ego vehicle listens for the transmissions and the reservations made by neighboring cabs. And by monitoring the reservations, the vehicle can estimate which resources in the selection window will not be available for future selection. By doing so, the vehicle is able to select, in principle, resources that have not been already selected by their neighbors and reserve them for a number of consecutive transmissions, of hopefully collision-free consecutive transmissions. So basically, the SPS scheme is based on the periodic reservation of resources, and its operation is ruled by two main important parameters: the resource reservation interval, or RRI, that corresponds to the time between consecutive reservations made by the ego vehicle, and the reselection counter, which corresponds to the total number of reservations. So, as you can see in this slide, after the first selection of resources, the vehicle periodically reserves the same set of subchannels, and for each reservation, the selection counter is decremented by 1. And when the selection counter expires, so reaches 0, the Eagle vehicle is forced to select new resources through a new resource selection instance. So, as you might have guessed, the SPS scheme perfectly works with fixed size periodic traffic due to its due to the nature of its periodic reservations. So, for example, if you imagine a scenario where we can set the generation period of the traffic tgen equal to the resource reservation interval, we can actually have a resource allocation scheme where the packet latency is guaranteed and that operates in a collision-free manner. In a collision-free manner, because by making reservations, vehicle will be able to notify their neighbors which resources will be occupied in the future, therefore allowing a collision-free selection of resources. However, the SPS limitation, the SPS scheme is far from being perfect. Far from being perfect from two main reasons. The first one is that during a resource selection, collisions can still occur, because if you imagine having two vehicles that generate two different packets at slots SG1 and SG2, if the selection window of these two vehicles overlaps, they will have a common set of candidate resources, which is in this case reported in this overlapping area here. And if the two vehicles select the same subchannel, then a collision will take place, but this collision will not happen individually. It will also persist for a number of consecutive and future transmissions. And therefore, the impact of a wrong selection of resources can persist over time and can lead to really detrimental effects. The second limitation of the SPS scheme is that it is poorly flexible. It is based on the periodic reservation of a fixed amount of subchannels. And so you can already start to guess what might happen when generated traffic is not really periodic and the packet size is not fixed. And in this slide, I want to show you what can happen when the packet size is not fixed and the vehicle is generating variable size packets. As I said before, SPS is based on the periodic reservation of a fixed amount of subchannels. So when we have variable size packets, a so-called size reselection can occur. A size reselection occurs whenever the generated packet doesn't fit in the reserved resources. What I mean is the following. Imagine that a vehicle generates a 200 bytes packet at slot SG1 and selects resources at SR1. What happens if the next packet is double in size, is 400 bytes? The currently reserved resources are not able to fit the new packet, and so the vehicle is forced to select a larger number of resources and to reserve this larger reservation. A larger reservation also means that if at some point a new packet is smaller in size, again 200 bytes against the 400 bytes reservation, then we will have a portion of the reserved resources, in this case one out of two subchannels, that will remain unutilized, therefore leading to a waste of resources. And what if the traffic is not perfectly periodic and is aperiodic, which, by the way, is a very realistic scenario since many V2X enabled applications do not generate periodic traffic, but rather generate aperiodic traffic, as we will see also in this presentation. As SPS is based on the periodic reservation of subchannels, when the traffic is aperiodic, the interarrival time between packets, the generation period, is unknown, and we cannot properly set the resource reservation interval. This leads to the so-called latency reselections, which are another type of inefficiency due to the poor flexibility of the SPS that leads to an increase in the total number of resource reselections. A latency reselection occurs whenever the current reservation is not able to respect the packet delay budget. As an example in this slide, imagine a vehicle generating a packet at slot SG1 and selecting resources at slot SR1. If the new packet generated at slot SG2 has a packet delay budget at this slot as limit, which occurs before the reservation, then the vehicle will be forced to select new resources within the packet delay budget as limit, and therefore trigger a latency reselection, so a new resource reselection mechanism. And as we have seen before, resource reselections can be particularly detrimental because during a every time that we perform a resource selection, then a packet collision can occur. And the new selected resources will be also reserved, but due to the aperiodicity of the traffic, we might also have reservations that do not have any packet to be transmitted and therefore are completely unutilized and wasted, as reported in this case. And so leading to another excessive waste of resources that affects the performance of the SPS scheme. In this slide, I have reported a couple of numerical results that show you actually the impact that variable size and aperiodic traffic can have on the performance of the SPS scheme. So as we said before, basically due to the mismatch between the generated traffic characteristics and the SPS reservation, we can have size reselections and latency reselections, which increase the total number of resource reselections, therefore eventually increasing the collision probability. And we can also have unutilized reservations that waste radio resources. And as a final result, the SPS performance can be significantly deteriorated. In the left side of this slide, you can see that what happens in the case of a low channel load. We have the blue curve, which refers to periodic fixed size traffic. And you can see that this blue curve is actually the curve able to achieve the highest packet reception ratio values, where the packet reception ratio actually measures the fraction of packets that can be correctly decoded by the receiving vehicle. And you see that with the black line, where the packet size is fixed, but the traffic is aperiodic, we already start to see a degradation in the performance, and the worst packet reception ratio performance is attained by the red line, which corresponds to aperiodic traffic with also variable size packets. And this situation is even more manifest if we move to the right side of the slide, where the channel load is larger. So the decrease in the scheduling accuracy performance of the SPS scheme associated with the aperiodicity and the variable size packets is even more evident. And you can see that actually there is a quite large gap between the black and the blue and the red and the blue curves. So what happens when we want to deal with a real world application, which can be cooperative awareness messages? Cooperative awareness messages are awareness messages that are transmitted as part of the phase 1, the awareness driving phase, and are awareness messages broadcasted by road users to inform other road users about their position, dynamics, and attributes. And we actually have two main categories of awareness messages: cooperative awareness messages, which are transmitted by cars and motorcycles, and VRU awareness messages, which are disseminated by VRUs like pedestrians, bicycles, and e-scooters. When it comes to cooperative awareness messages, we have some very specific generation rules defined by ETSI, the European Telecommunication Standards Institute, and that according to these generation rules, a new CAM is generated when one of the following conditions is satisfied. When the difference in the heading of the vehicle is larger than 4 degrees, when the distance traveled by the vehicle is larger than 4 meters, or when the difference in the speed of the vehicle is larger than 0.5 meters per second, or fourth, when a timeout condition is triggered, so when no message is generated by more than 1 second. So as you can see, these generation rules are really dependent on the dynamics of the generating vehicle. And as a result, the inter-arrival time, so the time between one packet and the next one, is really dependent on the vehicle dynamics. And the result of this strong dependence on the vehicle dynamics is that the generated traffic is far from being periodic. And as we demonstrated with real-world experiments and sumo simulations, the PMF, so the probability mass function of the interarrival time reported here on the left, is actually not concentrated on a single value, but is spread along the entire x-axis. In this case, for a urban scenario, you can see that the more frequent values are concentrated around 300 and 400 milliseconds, but also other values are possible. So demonstrating that actually the traffic is really far from being periodic. And as you can see on the right side of this slide, where I have reported the temporal evolution of the interarrival time, you can see that the interarrival time, so the generation period between consecutive messages, remains fixed, remains constant, only for a short number of consecutive packets. So as interarrival time between cooperative awareness messages, TCAM, is not fixed, but actually can have any value in the range between 100 and 1000 milliseconds, the key question now is, how can we effectively serve CAM traffic using the SPS algorithm? Or in other words, how can we properly configure the resource reservation interval, so the spacing between consecutive reservations, and the reselection counter, so the total number of reservations, in order to minimize the collision probability and improve the SPS performance? And actually, the solution relies on AI. AI, because the idea is to leverage AI to leverage the strong correlation between the interarrival time between cooperative awareness messages and the vehicle dynamics for predicting the temporal evolution of the interarrival time, and accordingly configure the two SPS parameters. And as an example, let's take this segment of the CAM trace. As you can see here, we can have 5 cooperative awareness messages with a interarrival time equal to 200, then 4 messages with the interarrival time equal to 300, and so on. So by leveraging the correlation between the vehicle dynamics and the CAM generation rules, the goal is to be able to predict these short sequences of packets with the same interarrival time, and accordingly configure the resource reservation interval and the reselection counter parameters. To do that, I actually, as part of my work, we define an additional AI-based traffic prediction layer that lies just above the MAC layer in order to optimize the SPS parameters, that works as follows. This AI-based traffic prediction layer takes as input the input features that will be leveraged by the AI mechanism in order to predict the traffic and accordingly optimize the reservation parameters. So by collecting the input features, the AI algorithm is able to predict the future sequence of CAMs, of cooperative awareness messages, and accordingly identify the best selection of RRI and reselection counter parameters that are directly fed to the reservation phase of the SPS mechanism in order to minimize the number of size reselection, latency reselections, and unutilized reservations. Regarding the implementation of this AI-enhanced SPS mechanism, the implementation, of course, is strongly dependent on the simulation environment that we considered. In my case, I consider a simulation environment based on Sumo, the traffic simulator, which mobility is based on car following models, basically. And therefore, in order to predict the vehicle dynamics, I considered as input features the trajectory, the speed, and the position of the generating vehicle, and the position and the speed of the preceding vehicle, formulating the task of predicting future cooperative awareness messages and the interarrival time between them as a classification problem, where we have 10 classes for each possible interarrival time value in the 100-1000 milliseconds range. And regarding the candidate machine learning classifiers that I considered for this prediction task, I here have listed the main simulation complexity of 3 of them: random forest, support vector machines, and KNN. And actually, I ended up selecting the KNN algorithm because it's the simplest one that requires no training phase and actually has a very quick prediction time. And so for this quite simple task, KNN was the one able to achieve the best performance in the shortest time. As you can see here in the slide, the KNN algorithm is able to correctly predict future interarrival time values with future interarrival time values between cooperative awareness messages with a prediction accuracy that is larger than 90%. So, for example, in the left-hand side, you can see that in the confusion map on the diagonal, we always have values larger than 90% for the prediction of the next interarrival time value. But also, if we extend the information horizon and we want to predict the sequence of 10 in a sequence of 10 consecutive interarrival time values, the diagonal here reports pretty high accuracy values, always very close to 90%. So here, by looking at these confusion maps, we can really see that the KNN algorithm, although being fairly simple, is actually able to correctly predict the interarrival time between consecutive messages. For the assessment and for testing and validating the proposed solution, I considered let's say suburban scenario extracted from OpenStreetMap and imported into Sumo, where the average vehicular density was 42 vehicles per kilometer and the vehicle speed was ranging from 50 to 100 kilometers. In terms of system configuration of NeuRadio V2X Mode 2 and the SPS mechanism, I considered a total of 4 subchannels and a modulation encoding scheme of QPSK 0.7 code rate and 2 different packet size values, 190 and 470 bytes, which are actually the most frequent packet size values encountered in experimental studies. And as a system-level simulation tool, I employed the More V2X simulator that I developed during my PhD, and I compared 3 different solutions. A ground truth solution, where we assume that we perfectly know the future evolution of the interarrival time, and so we are perfectly able to configure the RRI and reselection counter parameters, the KNN enhanced SPS, so the proposed AI enhanced SPS mechanism, and the legacy one, which employs a fixed RRI and a fixed reselection counter value. As you can see here in the slide, the proposed KNN enhanced SPS is able to drastically reduce the number of unutilized reservations and latency reselections. Actually, the total amount of unutilized reservations and latency reselections is reduced from 61 to 10%. And accordingly, we are able to significantly reduce the waste of resources and the collision probability. As you can see here, where, for example, on the left-hand side, for the smallest packet size, the collision probability of the black curve, which is the legacy solution with the resource reservation interval equal to 100 milliseconds, is the largest one, whereas the blue one, the KNN-based SPS mechanism, is always very close to the red one, to the ground truth curve, which represents the benchmark. And of course, the gap in the collision in terms of collision probability between the legacy solution, which is the black curve, and the proposed one in blue increases, because here the channel load increases and the collision probability increases as well. So the importance of accurately selecting the RRI and reselection counter parameters is critical in order to reduce the number of collisions and improve the scheduling accuracy of the SPS scheme. And actually, this improvement in terms of collision probability is also reflected in the packet reception ratio. So as I said before, in the total number of packets that can be correctly delivered to the intended receivers. And as you can see in this slide, as before, also in terms of packet reception ratio, the proposed KNN enhanced SPS is always very close to the red benchmark, the ground truth benchmark, demonstrating therefore that AI-enhanced scheduling, AI-enhanced SPS can really be a solution to disseminate real-world aperiodic traffic where there is a strong correlation between the generating vehicle dynamics and the characteristics of the generated traffic, therefore overcoming the SPS limitations in terms of flexibility. And again, in this slide, we can see that the gain of the proposed solution in blue increases with respect to the legacy SPS as we increase the packet size from 190 to 470 bytes due to a larger impact of the channel load and the collision probability. Last slide about the packet reception ratio deals with the possibility of comparing the proposed solution with different fixed RRI configuration strategies, because if we monitor the probability mass function of the generated CAM traffic in the simulated environment, we realize that 200 and 300 milliseconds are the most frequent inter-arrival time values for CAM traffic. So what about configuring the RRI equal to these two most frequent values? As you can see here on the right side, the blue solution, the blue curve, the proposed solution is able to outperform the SPS when configured also with these two more frequent fixed RRI values. And moreover, the proposed KNN SPS solution is not only able to outperform a fixed RRI strategy, but the KNN SPS doesn't require the a priori knowledge of the probability mass function of the generated traffic, but it can adapt the reservation parameters on the fly based on the characteristics of the generated traffic. So to conclude, in this presentation, I wanted to show you that a simple yet effective KNN SPS for the dissemination of cooperative awareness message traffic can really be effective in overcoming the limitations in terms of flexibility that affect distributed C V2X silent communications. Therefore, highlighting the potential of AI-enhanced resource reservations for improving the poor flexibility of the SPS strategy. And in a nutshell, AI-enhanced SPS is able to dynamically adjust the reservation parameters and reduce the size and the number of size and latency selections and unutilized reservations, thanks to an additional AI-based layer that is placed right before the MAC layer and is able to predict the characteristics of the generated traffic in terms of packet inter-arrival time and packet size. And I would also like to say that although this AI-based traffic prediction layer here was tested for CAM traffic, it can also be extended to other future V2X enabled applications like cooperative perception and cooperative driving, where there might be also in this case correlations between the characteristics of the generated traffic and the dynamics of the generating vehicle, therefore being really a potential for overcoming the limitations of the SPS strategy and really distribute and broadcast traffic in a more reliable manner. This concludes the presentation. I would like to thank you for your attention, and I'm available to take your questions.
Thank you, Luca. Thank you so much. And a wonderful presentation. We have a few questions. I will read one by one. And before that, I would like to ask one question for myself. I think the scheme that you presented is really nice. I mean, based on my experience with V2X, the thing that I was wondering while listening to your presentation was how easy it is to implement. So, if we are talking about the real system implementation, what do you think? How easy it would be?
Okay. Of course, the complexity of the of the implementation really depends on the environment that we consider. In my case, it was a fairly simple simulation environment based on simulations which are based on car following models. So we have a limited amount of features that can really influence the dynamics of the generated traffic. But I think that this type of approach can be extended also to more realistic scenarios where we have more features to consider, but it's definitely can be definitely extended to any real world application. And in terms of implementation, it's just about being able to collect the features that influence the driving of the vehicle in this case.
Yeah. And speaking of complex scenarios, there is another aspect. Like nowadays, we are talking a lot about like AI, ML, and training the models. So, for example, how could we train the models for this kind of scheduling scheme to improve over time? So basically, using the recorded data to train our system, and using that kind of information to improve our models. I think that can be something for to look into future. But do you
Yeah,
think that that is possible, or?
yeah, definitely. And I think that a possible real world implementation would be also to leverage edge computing to collect and centralize the data collected by different vehicles in a central model that is trained by a centralized infrastructure and then later distributed in order to be the a more accurate model, able to generalize better based on the statistics collected not by the single vehicle but collected by all vehicles.
Mhm. Perfect. So we have a question from Alexei. He says, how do you predict right value of RC? For each packet, is it different fixed value for RC?
RC means selection counter, I think.
Yeah, I think so.
Yeah. Okay. In this case, the selection counter is based the the selection of the best selection counter value is based on the predictions provided by the AI-based traffic prediction layer. So, if the traffic prediction layer predicts that there will be a sequence of 5 consecutive cooperative awareness messages with the same interval time, then the reselection counter will be set equal to 5 in this simple example. And then, so prediction by prediction, the reselection counter will be adapted based on that.
Good. Then we have a few questions, so we go one by one for each of those. There is another one. What is the density of vehicles on slide 30?
42 vehicles per kilometer.
42 per kilometer. And you were generating using like what statistical model?
I was generating these vehicles
Poisson distributed or?
yeah, with a random distribution, a uniform distribution where the time between two generated vehicles was a random variable between 0 and 1 second. So at each road of this network represented here, a new vehicle was generated every second with a uniform probability.
Okay. But just I think what I have seen in the past is Poisson distribution is also an
Yeah,
model.
definitely. Yeah. I mean, there are also real world traffic traces that
Exactly.
can be exploited, but yeah,
Uh,
there might be multiple solutions.
True. Then we have all of these results were obtained with persistence probability equal to 0.
Yeah,
Good.
yeah, absolutely. Yeah. And persistent probability equal to 0 has been demonstrated in other papers that have not reported in this presentation to be the optimal solution for the SPS operation. Of course, it could be worthwhile to investigate what happens with
Mm,
other persistent probability values, but yeah, I think that there are already plenty of studies on that.
clear. Okay. Then we have would it be too difficult to manage and predict the large amount of samples using KNN? For example,
Yeah,
large data set, wouldn't it delay the processing?
Yeah, absolutely. Yeah, I mean, yeah, absolutely. KNN in this case was the best solution for me. I mean, I'm not saying that KNN is the best solution overall. I mean, it depends on the simulation environment and on each implementation. In my case, since this was quite simple, let's say simulation environment where the number of features was quite limited, the KNN algorithm was the best one for me. But of course, there might be. I mean, there for sure there are better machine learning algorithms. I know that there is people working on LSTM algorithms for predicting cam traffic. Yeah, there of course there can be better algorithms. Yeah, but in this work, the focus, I think, it's not really on the machine learning on the specific machine learning algorithm that we select for predicting the traffic, but it's really on the potential of integrating AI into the reservation of resources.
Yeah, and I think there could be another interesting aspect to it, that we are not, maybe in the real world we may not be trying to do it in the real time. So it could be that you use the data set, you come up with certain model, you come up with some conclusions, and utilize those conclusions for a specific period of time. Meanwhile, in the back end, you can update the
Yeah,
model, upload,
absolutely,
depending on
absolutely.
the condition of the road. So it could be like, a prediction based on the prior data, utilize the model. So it may not be real time. That is why, like, we could afford some complexity or some data processing in the back end.
Yeah, totally agree with you, Temur. Yeah.
Good. Then we also have another question from Sayed Mursaleen. Thank you for watching. So he also just adds on to the previous question related to KNN. He says that the data set was basically consistent for few samples, right? Like, if he wants your confirmation, and I think
Yeah.
only 1,000 samples, would it be okay for analysis? Like, is it good enough?
Oh my God. I mean, I cannot really tell if 1,000 samples might be enough to generalize accurately. As I said, this is quite a simple simulation environment, so maybe 1,000, 2,000, 3,000 samples might be already okay. Of course, as the complexity of the environment increases, then you will need more samples, more sophisticated machine learning algorithms, and so on.
Perfect. Thank you. So he's thanking you. He got the
Thank you.
thing. So really appreciate, Luca. I think it was wonderful, and we would be happy to have you at this forum once again with newer results. So
Thank you very much, Taimur, and thank you everybody for watching.
thank you. Thanks for today. With
Thank
that, we would like to close the webinar. Anyone who is listening and has some interesting results to share. So this forum is all for the young professionals. So the whole point is we bring the young professional to the front, their work, and get them recognition. So that is why we started this webinar series, and I would really appreciate all of you to step up, write me an email. You can search for the VTS IEEE VTS webpage, and underneath you can see young professionals. Come up with any proposal, any ideas, and we will be happy to work together. With that, thank you so much for today. Thanks, Luca.